Now that we've seen how basic data types are represented in Java, let's turn our attention to the differences between pointers and references, pointers in C and references in Java. We're going to take a look at that in much more detail than we have so far. And then we're also going to look at how we organize the code for our objects in Java. Where do we find the methods associated with each of the objects? Pointers to fields in C, we've seen before, just in the last video actually. And we've seen that the common construct is to have a pointer to a struct, dereference it, add an offset to a particular field. And this is such a common situation of referencing a field in an object to which we have a pointer, to a struct to which we have a pointer, that we have a shorthand in C, R arrow A, okay, which encapsulates that dereference there. In Java, since all variables are references to objects, we don't have to worry about that explicit dereference. Instead, we always dereference by default, so we can use a simpler notation, just r.a, to refer to a field within an object. All right? But the thing to remember is that what's actually going on here is we are taking the reference or pointer to the object, going to that location, adding the offset, and finding that field that way. Let's take a look at how we do casting in C and contrast that to what we do in what we can do in Java. This is an example of code from a memory allocation program, similar to the things we've been talking about in the previous section. And what we're going to do here is take a pointer to a block of memory. We're going to cast it as a simple pointer, a byte pointer, add an offset of number of bytes. This will point us to a new location in memory, and then recast that as a struct of type block info. Now, the reason we do this is this would be in a case where, for example, we have a block of memory and we want to break it into two blocks because we want to allocate one to something and have the remaining block left over. So remember that our block definitions included a couple of few variables. The first one, an integer to represent the size and the tags of the block, and then two pointers to the next and previous blocks in memory. So the way this ends up looking in our memory is we started off with a pointer to a block that had those three fields at the front, right, the two pointers and the size and tag. And we've now offset that by some number of bytes x and created a new area in memory that we're going to interpret as a block info struct. The casting is equivalent to putting a lens over the memory and saying, look at this memory at this location. We are going to view that as a block info. So that means we will interpret the bits in memory in the first 4 bytes as the size and tag, in the next 4 bytes as the next pointer, and the next 4 bytes as the previous pointer. It's purely a reinterpretation of what is in memory. And then, of course, we have to make sure we put the right values there, the right bits there to really be those pointers and that size. Okay, but we can do this to any region of memory and cast it into whatever struct we want. All we're doing is instructing the system to view that memory in that way, to look at it through that lens. In Java, on the other hand, we can only have pointers or references to objects. We cannot just point to an arbitrary part of memory. So in this case, I want to show an example of an object hierarchy. We started off with our main object. We defined the parent object, and then 2 subclasses of that called sister and brother. Okay. This code fragment here shows things that are legal and illegal in Java. The ones that are bad are shown in red. But let's take a look at the beginning of this code. We've just defined 3 objects here, one of type parent, one of type sister, and one of type brother, using the new construct, and assigned them to a variable of that type. Pretty straightforward. Okay, now let's take a look at our first cast. We've created a new object called sister, but put it into a pointer or a reference to an object of type parent. And that's okay. Why is that okay? Well, because sister inherits everything from parent, so it has all of parent's fields and methods. So we can still use all those things if we refer to the object as a parent. So we can get away with that. As an example, if we went in the other direction, if we had created a new parent and tried to put it into a variable of type sister, we have a problem because sister has things that parent doesn't have. So when we try to cast that parent as sister, we're missing some things. What are we missing? Well, at the very least, we're missing this variable hers that is expected to be in a sister object. Parent didn't have that. Parent only had address. Also, there might be some methods that go along with the object sister that we wouldn't be inheriting either. So that is the wrong direction to be able to do a cast. Let's take a look at another example just above this one. If we create a new object called brother, try to cast it as a sister, that doesn't work either. And the reason in this case is, of course, that brother also has a different variable called his that we don't know where to put if we move it to the type sister. So not only is it missing hers, but it has this other thing, his, that sister doesn't know what to do with. Okay. Let's take a look at yet another one. Here you'll notice that we've taken our parent object, tried to cast it as brother and assign it to a brother variable. Well, that's not going to work either because that parent object does not contain all the elements of brother. It's missing the variable his in this case. Here's one that does work. If we take a parent object, cast it as sister, and then assign it to another variable of type sister. Why does that one work? Well, this one turns out to work because this original object, P2, started out as something of type sister. You'll notice that P2 was assigned P1, and P1 was originally an object of type sister that was cast as a parent, but it started its life as an object of type sister, so that it has everything a sister needs, a sister object needs. And so therefore that cast works out. So you can see things can get pretty elaborate in Java, but the basic idea is that to be able to do a cast, the objects have to be compatible. They have to have the same variables in both types and the same methods available so that they can be converted. Let's take a look at objects in Java in a little bit more detail. We're going to run through this example for a couple of slides here. We defined a class called point. It has two fields, x and y coordinates. It has a constructor, a function that is called, or a method that is called whenever we create a new object of this type. And what this one does is just initialize those coordinates to 0. It also has a method called samePlace, which takes one argument, another point, and compares the x coordinates and y coordinates and sees if they're the same, logically ANDing them together. When we create a new one of these points, this is what it would look like in our code. We would say new point object, and this will cause the memory allocation to find a place to create this object, namely a place to store these two variables that it's going to need. And it's going to return a reference to this new location in memory, this new object, and then run the point constructor code on that object. That will cause those variables to be initialized, and then that reference will be stored in the variable new point, which is of type point. So these are compatible. So let's review that again. When we call new, what's happened is we've allocated space for the data fields, in this case x and y, but we've also done one other thing. Here's x and y, those two doubles that we needed, but we've also allocated a pointer at the beginning of the object to what's called a V-table or virtual table. The V-table is shared across, the V-table pointer is the same for all the objects of this class, all the points we might create. What it does is it points to another region in memory where we've stored the pointers to the code we need for this type of object. In this case, there were two pieces of code, two methods. One was the constructor, so we need a pointer to the constructor code, and then same place. We need a pointer to the code for that method. You'll notice that this is using a level of indirection, actually two levels. Inside of the object that we've allocated, we've left a pointer so that we can get to the table of pointers to the code. That's one level of indirection. Then when we go to that location in memory, we'll find another pointer, another level of indirection, to the code for the constructor, to the code from same place. And by convention, we always put the pointer to the constructor first. Okay. Once we're done with the object, if we don't need it anymore in our code and lose all references to it, our garbage collection routines will find it, find this place in memory, and say, nothing seems to be referencing it. We can reclaim this space so we can use it for other things. And it will take back the space that had been allocated for the object. However, the space allocated for the V-table will continue to reside in memory because we might create a new point sometime later. This space, remember, is not reclaimed for the object. That's a space that is allocated once for every object of this type. They will all be pointing to the same V-table. All right, next step. Let's say we've created this new point. We have a place in memory for its x and y variables, and we have a V-table pointer. And now what we're going to do is call this object constructor, that first method, that piece of code that is going to run on to initialize this object. To do that, what we're going to do is call the function constructor with a single argument, which is going to be the pointer to the object we've just allocated in memory, okay? Which contains those two fields. The constructor code is going to run with a pointer to this location, so it will know that x is the very next element and that y is the one after that. And the compiler will set things up so that those offsets are appropriately calculated and we can put the 0 values in those two locations. Now, where does the code for the other methods go? How do we find that? Well, methods in Java are just functions, as in C, but as you've noticed from the previous slide, there's an argument that's implicit. Although we had defined constructor without any arguments, the constructor without any arguments, we did give it an argument which was the newly allocated space in memory. This pointer is always referred to by the name this in Java. That's a built-in keyword that says we're talking about the reference to the current object. All right, so all of our methods really have this as the first argument. So the method samePlace, which was defined with a single argument, p, really has two arguments, this and p. So those two pointers point to those two objects in memory. And if we had equivalent C code, it would look like this. We would follow the this pointer to the element x, the p pointer to the element x, compare those two, do the same thing for the y's, and then do the logical AND. Okay, so this is how we find the variables, and the way we go about finding the code is through the V-table pointer. How do we subclass an object? Well, here you'll notice I've created a new class called point subclass that extends point. It has a couple of different things from point. One, it has a new element called a new field. It also overrides the samePlace method that we had previously defined for points. And it has a totally new method called sayHi. So where does this new new element go, this new integer, a new field? And where does the pointer to the two other methods, the code for the two other methods go? How do we find those? All right, so what we're going to do is just add these fields and pointers onto the ends of the object in memory and to the end of the vtable. So let's take a look at what the map in memory is going to look like. Our new object is going to look just like point, except that it has an extra int at the end. So when we allocate space for this object, we need a little bit more space to also be able to store a new field. The reason we tack it on at the end is that if we ever want to cast this as a point, we don't have to worry about the offsets being different than they were before, so that x and y are still in the same relative positions. The vtable for this object is going to be different than the vtable for the previous object. This vtable has 3 elements, not 2, because we have a constructor, we have same place, but we also have say hi. Now, where do we point to? Well, constructor is just going to inherit the previous constructor. We didn't change that at all. So this is going to be a pointer to the same region of code, the same routine that we had for point. Same place, though, is going to point to this new code that we're using to override the old version of same place. And say hi will, of course, point to a totally different area. So we've tacked on a new field at the end of the object definition, extra space in memory for that. We have a new vtable for point subclass. It is not the same vtable as point because this has different methods associated with it. However, we are reusing the code for the constructor by pointing to the same procedure in memory. Same place points to a new piece of code for this new same place. And of course, we have a pointer for the new code for say hi.